All right, let's go.
Okay, I'm ready. Do now. Draw a diagram of a heat engine. Is that the one with the circle and the lines? Yes. With 150 joules of heat flowing in, 35 joules of work being done. How much heat is wasted? 115 joules. Is that right?
Boom.
An engine has an input of heat energy of that many joules. It does.
Yeah, I'm not doing that.
So same. I think we already saw that one. I think it's 8,000 something. Okay. We did that one too. In moving into a dormitory, a student does that many joules of work and loses that many joules of internal energy. What is W, delta U, and Q? So we add them up this time?
We are heat engines.
Yeah.
We as humans are heat engines. Our sweat is the wasted energy.
Uh-huh.
So does
4,200 and 4,200? Is that my math?
4200.
Zero, yeah. Okay. So the Q
Work
would be
is that.
yeah. The delta U is that part, and then the Q you add them up together.
Yeah. 6 plus 2 is 8. 1 plus 4 is 58,000 joules.
Bada boom. Okay.
Okay. Now we are heat engines, and there are all kinds of diets. There's the Jenny Craig, there's the, I don't know, they got all these diets on television.
The Atkins, the paleo.
There's the high carb, the low carb, the no carb, the high protein, no protein.
High fat,
There's
keto.
a billion of them. There's only one diet that works, and it's the first law of thermodynamics diet. That is the amount of work that you put out. Wait a minute. The number of calories you take in food. That's the energy you take in.
What is that? QM sub M? Oh, in.
Is equal to the change in you.
Mm-hmm.
If you take in more than you put out, you get bigger.
Mm-hmm.
If you put out more than you take in, you get smaller. Mr. Boykin is proud to say that since March 1st, he's lost 11 pounds. Why have I done that? It's not by any frickin' diet. I'm not taking in as much.
Mm-hmm.
It's about the same amount of this. Reduce that, less me.
Mm-hmm.
That's the first law of thermodynamics diet.
Mm-hmm. An objective. You demonstrate the ability to identify high and low entropy states by giving examples.
Okay? I don't know what the hell entropy is. Okay? The second law of thermodynamics refers to the direction of natural processes. Question. Does time have a direction?
It's all relative. I don't know.
Does time have a direction?
It's supposed to be, ideally it's linear. So
Linear is a shape.
Yeah.
That's not a direction.
So
Does time have a direction?
I don't know. Yes? No?
Well, can you make time go backwards?
No.
Is
So it does
possible
have a
to get
direction.
time to go backwards?
No.
So time has a direction. It's inexorable. At our scale, at the macroscopic scale, time only goes one direction. I want you to know that in quantum mechanics, it's possible for time to go backwards, but only for electrons. All right? Okay, so I'm going to make a series of statements that tell what the second law of thermodynamics is, rather than just say one. Heat will not flow naturally from a colder body to a warmer body. Yeah. If you buy a soda and put it outside on a 100-degree day, the temperature of the soda will never go down.
Mm-hmm.
Here's another statement. Heat cannot be transformed completely into mechanical work. Can't do it. You can't get, if you're putting heat in and you're getting work out, you're also heating up the device.
Mm-hmm.
All right? You can't transform all heat into mechanical work. Notice that we're moving along here. Here's another statement. Natural systems tend to proceed toward a state of greater disorder. What the deuce is disorder?
What?
Yeah. Okay, well, we need to look at some examples of ordered and disordered systems. Okay, this is an ordered system. It's a sugar cube in water. There is that which is sugar, that which is water. They're organized. All the sugar is here, all the water is there, everything is where it belongs. Okay, but what happens if you drop a sugar cube into water?
Mm-hmm.
It's disordered. Now, instead of all the sugar being one place, all the water being another place, they're all mixed together. That's disordered. This is high entropy. This is low entropy, whatever entropy is.
Mm-hmm.
Ordered. You have a cold cube in warm water. That's what we had earlier. When we first dropped that thing in there, there was that which was cold. There is no such thing as cold. There was that which was cold, it was where the cube was, and there was that which was warm, that's where the water was. They were separated.
Mm-hmm.
That's low entropy, high order. Okay, however, as time went on, heat flowed until everything was at the same temperature.
Mm-hmm.
Heat flowed out of the warmer water into the low temperature cube until they're the same temperature. Now there's no separation between hot and cold. Now everything's the same. That's disordered. That's high entropy. The stuff is spread all over the place.
Mm-hmm.
A beak of water next to a bottle of food coloring, and I would have this. I'd always have hot water,
Mm-hmm. And then
and I take I drop one drop of food coloring in it. Okay. Before there's that which was red and that which was clear. All right, that was ordered. And when I first dropped it in, there was the drop right there, and it was red, and then it goes down, and there's that which is red, and that's ordered. That's low entropy. However, after 15 or 20 minutes, the whole thing is red. All right, that's disorder.
so it goes
That's
from order
high
to disorder, low to high entropy.
Okay, ordered. A match in oxygen in the air. There's that which is match. There's that which is air. Okay, all I got to do is give it a shove. I give it a shove, and then that which is match. That which is match.
Yeah.
That which is match. And what happens is, this is a beautiful demonstration, is that over time the kids in the front smell it,
Yeah.
and the kids in the back smell it. Diffusion.
Yeah.
Okay, so match, that's ordered, that's high entropy, and then the chemicals in the match react with the oxygen and spread around the room. That's disordered. That's high entropy. And you're beginning to develop, so you're beginning to see that there's a disconnect between the way you normally think of things. You think as ordered, that's high, that's and disordered, that's a mess, that's low. Boulder at the top of the hill, it's up here, and that's an ordered situation. How did it get there? Well, somebody built it, moved it up there. Disordered, gravity pulls the boulder down the hill to the bottom of the hill. That's high entropy. What does it take to go backwards?
A lot of energy.
Absolutely. I ain't doing it. Ordered, rake pile of leaves. In the fall, you got leaves everywhere. That's a mess in the yard. Somebody's got to do some work. They put all the leaves in one spot. That's nice and ordered. That looks nice. We'll put it in the trash or whatever. That's low entropy. However, If you have little kids in the neighborhood that like to play in leaves,
It's only natural that.
and you can't stop it. That's disorder.
And then it takes,
or the wind blows.
and then it takes you energy to put it back into that pile too.
So you're beginning to see the
Yeah.
pattern. Order a neat house before company comes. And I asked the kids, how many of you have a bunch of cousins? Aunts and uncles and cousins. They got a bunch of them. Okay, so your parents, drive you like slaves. Clean up that room,
Yeah.
And so you get everything nice and neat. The company comes, and then I don't have to explain what happens. You got the 3 and the 4-year-olds are in your closet, and they got half of it on the floor. That's a disorder. That's high entropy. So it takes work. It takes energy to go from disorder to order. Everybody agrees with that, especially at that last example. Entropy is the measure of disorder. It's how chaotic things are. More entropy, more chaos. Less entropy, less chaos. And the second law of thermodynamics, which we can now state, is that the entropy of the universe increases in every natural process.
Because it takes less energy to do that. It's less resistance.
You leave things alone, things go to hell.
Yeah.
And it's like, and then I do a thing with the kids. I say, why don't you get in there and clean up that room? The place is like a pigsty. How can you stand living there? But Ma, it's a second law of thermodynamics. Don't you know? The entropy of the universe increases in every natural process. It's natural for my room to be like this. Don't talk back to me!
Yeah. So then you ask them, what is entropy?
At this point, they should have a pretty good idea. And then I ask them at their tables to give an example of a high entropy, low entropy. So come up with your own, that's something we have, and then we go around and talk about it. When you put an ice cube in warm soda, why won't the soda get warmer and the ice get colder? Don't use the 0th law. Because the ice and water are an ordered situation. And the natural progression of things without putting energy in is toward disorder. So the ice gets warmer because heat flows in, and the soda gets colder because heat flows out. What does a refrigerator do? In terms of work and energy flow, what happens when you put a warm soda in the refrigerator? Put the warm soda in there.
Gets colder.
It's at a lower temperature. Heat flows out of the soda and into the refrigerator. And what does the refrigerator do with all that heat?
Takes it and puts it somewhere else, right? Read about refrigerators.
If you have a refrigerator and it has the coils on the bottom, when you walk by, you can feel the warm air.
Yeah. It just pushes it out. Is that what it does?
What it does is it takes the heat from the inside and uses electrical energy to pump that heat out.
Yeah.
And what it does is it has an evaporator that has that has a liquid, and inside the refrigerator, it evaporates it. It expands into a gas. As it does that, it lowers the temperature, and that expanded gas absorbs heat and then gets compressed. And the heat that is taken out of the refrigerator by that expanded gas gets compressed and goes. We don't need to talk about all the details.
And boom.
All right, so that's regular physics.
And if you just open the, click on the folder with the the normal one.
This one?
Yep. And then it's just, and if you go to like the 10th thing down, it's called it's called CSET Study Materials. On the left, the folder right there. And then it's called Second Law. It's the third from the top. Yeah, that's the AP one. Bada boom.
So here's a toolbox at this point because we're getting near the test. Here's all the stuff we've got and the stuff that they should know, including the This is for moles. This is for the number of particles.
Mm-hmm.
Okay, ideal gas law. We talked about the average kinetic energy of the particles. The root mean squared velocity, which we don't need to talk about. Okay, it's time to have a direction. We've already talked about that. Why?
Can't go backward.
Can't go backwards. Second law of thermodynamics refers to the direction of natural processes. And once again, Clausius, heat flows naturally. This is what we saw. It will not flow spontaneously from a cold to a hot. And then now we get into the Industrial Revolution. Engine takes heat, converts some of it into work, and wastes the rest. That's
Boom.
our heat engine thing. Blah, 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 blah. No device is possible whose sole effect is to transform a given amount of heat to work. This is Kelvin, this is Planck. Now we're in the late 1800s, early 1900s. Okay, you can't convert heat into work. It's impossible to build a perpetual motion machine. Why? Second law of thermodynamics.
Mm-hmm.
Because if something's moving, there's going to be friction.
Some of it's going to be wasted.
Yeah. Okay, now this is why we're doing this. The efficiency of heat engine compares how much work is done to how much heat went in. Okay, is that possible?
Mm-mm.
No. So it's always going to be work over the quantity of heat in. If this is the same, it's going to be 1.
Mm-hmm.
But it's never 1. In fact, in gasoline engines, it's about 20%. So the energy efficiency is defined as this. And we use lowercase e for efficiency.
So if you know the work and you know the was that the Q out or what is it? Is it
Q
in? And you know the Q in, then
Did it
you
say
can
Q
figure
out?
out the. I thought it. Go back real quick.
Q hot.
Oh, Q hot, not out.
Yeah, and so
Oh, and that's the hotter temperature, right? That's the Q in. Hot, cold. And you can find the efficiency and you know what, so what do you do with that? You just know the efficiency, or you can.
let's find out. A reversible process is one where you can return the systems and surroundings to exactly the same state.
Good luck.
Good luck with that. Now we did that with our syringe and the water baths, but we had to do some manipulation in order to do that. Okay, Carnot heat engine is ideal and reversible and defines maximum possible efficiency. Okay, this is an ideal situation. And this guy's name was Sadi Carnot.
Sadie.
S-A-D-I. He's a French guy.
It's my dog's first name.
Okay. Lord Kelvin, who gave us the temperature scale, equated heat to temperature and used temperature to define efficiency. So here's another way to define efficiency. That's the.
Oh, that's the.
And I think we saw that earlier.
We saw like it was like 400 and 800 and 300, and then we would have divided by 800. So 500 divided by. I see. Okay. So it's not going to get you the same answer, but it's just another way to talk about it. Or is it
Check
or is
it
it
out.
equal?
Now we've got an equation
Uh-huh.
where this is efficiency, that's efficiency. We can equate these to each other.
Are they equal and they get you the same answer?
Well, it's a definition of efficiency.
Okay, so it will.
So if you know the temperatures and you know the quantity of heat in, you can solve for the work.
Yeah,
You can
okay.
solve it.
Cool.
Oh, there's the same thing.
Yeah, that's what I was saying. So 800 minus 300. Wait, heat engine would.
Okay, so we've got high temperature.
Yeah, and then low temperature.
And we've got
So it's just 500 divided by 800?
So while running, it extracts
Times.
400 joules. So that's the QN.
Yeah. Okay, so you just do 500 divided by 800 times 400.
So what we need to do is how much work we're going to get.
Yeah.
All right, because what we're going to have is, you know, and that's what they're asking.
Yeah.
How much energy is expelled to the low temperature reservoir? So this is 400 joules. We need to find out how much of that is a W work, and we just do this by multiplying times Q.
Mm-hmm.
So that's going to be is 800 times 400, no, times 300
Don't we? Oh, times, not the minus.
Kelvin
Divided by.
joules is 400 joules divided by, and that is, yeah, it's multiplication, right? I didn't screw up, did I?
I don't know. I think I
had the
was.
same question you did.
Oh no, it is subtraction. That makes it easier.
And it makes more sense.
Yeah.
So the temperature hot is 800 Kelvin. So 800 minus 300 is 500 Kelvin. And because I was thinking about that's gonna be Kelvin squared. What the hell is that? and don't units solve
Yeah.
problems for us?
They do.
So 5 times 4 is 20.
200.
So 5 times 4 is 20. So that's 201, 2, 3, 4. That's 200,000 divided by 800. 22. I can't do that.
Me neither.
2000
2 point something.
divided by 800 divided by 8. $250 joules.
Boom.
So the work is 250 joules.
Mm-hmm.
Got 250 joules of work.
And then you can figure out what the.
Q out is 150, right?
Uh-huh. And if you just want to figure out, so if you want to figure out the efficiency, so you just do the work divided by the QN. Okay.
Well, we could have found the efficiency first.
Yeah.
And
Yeah.
that would have been 5/8,
Yeah.
which is 5.625, 0.5625. So you multiply 0.5625 times 400, and you get that.
Wait. Say it again. Wait.
800 minus 300 is 500.
Yeah.
500 divided by 800 is 6.25. I said 6.125. It's 6.25.
Oh, and that's
so the efficiency is 0.625.
Okay.
See, this is nice about having the.
Yeah, you can see it.
Everybody can see it. So now you take 400 times that number.
Oh.
250.
10% remaining.
We just did this, and that's all.
Great. Now, so you could also do, if they gave you work, that you could do 250 divided by 400 multiplied by 100, right?
Yeah.
Okay, just making sure.
And $250 divided by 400. 250 divided by 400 should be 0.625.
So 62.5.
So there's two ways of finding the efficiency. Although we're using the result of a calculation to prove something. And
So you might as well use that. Yeah. Okay, that makes sense.